Article 1. The impact of agricultural runoff on water quality. Agricultural runoff occurs when rainwater or irrigation water flows over agricultural fields, picking up soil, nutrients, and pollutants as it moves. This water eventually makes its way into nearby streams, rivers, lakes, and other water bodies. Fertilizers, especially nitrogen and phosphorus, are commonly used to enhance crop growth, but excess amounts can wash away into water systems. Similarly, pesticides used to protect crops from pests and diseases can also be carried by runoff. These substances, while beneficial to agriculture, become harmful when they contaminate aquatic ecosystems. One of the most significant consequences of agricultural runoff is eutrophication, a process in which water bodies become enriched with nutrients, leading to excessive growth of algae. Algal blooms can block sunlight from reaching aquatic plants and reduce the oxygen levels in water as the algae decompose. This process, known as hypoxia, creates dead zones where aquatic life cannot survive. Eutrophication is a widespread problem in both freshwater and marine environments, with the Gulf of Mexico's dead zone being one of the largest and most well-known examples. Besides affecting aquatic ecosystems, agricultural runoff poses risks to human health. Nitrate contamination in drinking water is a major concern, particularly in rural areas where groundwater is the primary source of drinking water. High levels of nitrates can lead to conditions such as methemoglobinemia or blue baby syndrome, which affects infants and impairs their ability to carry oxygen in the blood. Pesticide contamination of water sources can also cause long-term health issues, including cancer and endocrine disruption. Economically, the impact of agricultural runoff is significant. The cost of cleaning up polluted water, restoring damaged ecosystems, and addressing public health issues place a heavy financial burden on governments and local communities. For instance, the annual cost of dealing with water pollution in the United States is estimated to be in the billions of dollars. Additionally, industries that rely on clean water, such as fisheries and tourism, suffer when water quality is compromised by agricultural runoff. The sources of agricultural runoff are varied and complex. It is not only large-scale industrial farms that contribute to the problem. Small farms and even urban gardens can also produce runoff. Factors such as soil type, slope, and weather conditions influence the amount of runoff generated. Moreover, the timing and method of fertilizer and pesticide application play a crucial role in determining how much of these substances end up in water bodies. Efforts to reduce agricultural runoff and its effects are ongoing. One of the most effective strategies is the implementation of best management practice (BMPS) that aim to minimize water pollution from agriculture. BMPS include techniques like crop rotation, cover cropping, and the creation of buffer strips along waterways to absorb pollutants before they reach water bodies. Additionally, more precise application of fertilizers and pesticides using technologies such as GPS-guided machinery can help reduce the amount of chemicals that are lost to runoff. Regulatory approaches have also been employed to address agricultural runoff. In many countries, laws and regulations are in place to limit the amount of nutrients and chemicals that can be applied to fields. For example, the European Union's Nitrates Directive aims to prevent water pollution by controlling nitrate use in agriculture. In the United States, the Clean Water Act includes provisions for controlling pollution from non-point sources, such as agricultural runoff. Despite these efforts, challenges remain. Climate change, for instance, is expected to exacerbate the problem of agricultural runoff as more intense rainfall events increase the likelihood of runoff. Additionally, the growing demand for food production puts pressure on farmers to use more fertilizers and pesticides, which in turn increases the potential for runoff. As such, balancing the need for agricultural productivity with environmental protection will continue to be a key challenge for policymakers and farmers alike. In conclusion, agricultural runoff is a major contributor to water pollution with far-reaching consequences for ecosystems, human health, and the economy, while efforts to mitigate its effects are underway. Addressing the root causes of runoff, such as the overuse of fertilizers and pesticides, is essential. Sustainable farming practices, supported by regulatory measures and technological innovations, offer a promising path forward in reducing the impact of agricultural runoff on water quality. Article 2. The history and cultural significance of the Great Mosque of Cordoba. The Great Mosque of Cordoba, located in the southern Spanish region of Andalusia, stands as one of the most significant architectural achievements of the medieval Islamic world. Originally constructed as a mosque in 784 AD under the direction of Abd al-Rahman I, the first Umayyad ruler of Spain, the building has undergone several transformations throughout history. It was converted into a Catholic cathedral in 1236 following the Reconquista by the Christian forces. Despite this conversion, the mosque has retained much of its original Islamic architectural integrity, blending Islamic and Christian elements into a unique cultural artifact. The original mosque's layout was vast, with a prayer hall supported by rows of double-tiered arches, an innovative design at the time. These arches, consisting of alternating red and white stone, have become one of the defining visual elements of the structure. The expansive courtyard, known as the Patio Los Naranjos, core of the orange trees, added to the serene atmosphere of the mosque, providing a space for prayer and reflection. Over the centuries, additional expansions, particularly under rulers like Abd al-Rahman I and al-Hakam I, increased the size and grandeur of the mosque. The mosque's design was influenced by earlier Islamic architecture, including elements drawn from the Umayyad Mosque of Damascus. However, the architects also incorporated Roman and Visigothic components, a testament to the multicultural influences present in medieval Spain. The blending of these architectural traditions created a space that transcended its religious function, serving as a symbol of the diverse cultural heritage of the region. After the Christian conquest of Cordoba in 1236, the mosque was consecrated as a Catholic cathedral, and modifications began to reflect its new religious purpose. The most significant transformation occurred in the 16th century when a Renaissance-style nave was inserted into the middle of the mosque. This addition, though controversial, has been viewed by some as an example of the region's cultural hybridity, while others see it as an imposition on the original Islamic structure. Beyond its architectural significance, the Great Mosque of Cordoba holds immense cultural and symbolic importance. During the height of its use as a mosque, it was a center of learning and religious scholarship. The mosque represented not only the power of the Umayyad dynasty in Spain, but also the broader Islamic Golden Age, a period marked by significant advancements in science, medicine, philosophy, and art. It served as a physical manifestation of the Islamic world's intellectual and cultural achievements during the medieval period. In modern times, the Great Mosque of Cordoba remains a powerful symbol of cultural coexistence. Its dual identity as both a mosque and a cathedral highlights the historical intersections between Islam and Christianity in Spain. Its shared history is commemorated today through the site's designation as a UNESCO World Heritage Site. Tourists and scholars alike are drawn to the mosque for its architectural beauty and its representation of a complex, intertwined cultural legacy. The building's symbolic significance has not been without controversy. Debates continue regarding its religious identity. Some argue that the mosque should be restored to its original Islamic purpose, while others believe it should remain a Catholic cathedral. This tension mirrors broader discussions about cultural heritage, identity, and the interpretation of history. Ultimately, the Great Mosque of Cordoba stands as more than just a religious structure. It is a testament to the fluidity of cultural and religious identities and serves as a reminder of the rich, multifaceted history of Spain. Its enduring beauty and significance lie not just in its physical form, but in its ability to encapsulate the cultural dialogue between different civilizations over time. Article 3. The development and impact of electric ferries. The maritime transportation sector is critical to global trade and daily commuting in many regions. However, this sector has traditionally been one of the largest contributors to carbon emissions, primarily due to the reliance on diesel-powered ferries and other ships. In recent years, there has been a growing push to reduce the environmental impact of marine transport, leading to the development of electric ferries. These vessels are powered by electricity rather than traditional fossil fuels, making them a cleaner and more sustainable option for transportation over water. The move towards electric ferries is part of a broader trend in the electrification of transport, which is aimed at reducing greenhouse gas emissions and promoting environmental sustainability. The technology behind electric ferries is based on battery electric propulsion systems. These systems are powered by large lithium-ion batteries, similar to those found in electric cars, but on a much larger scale. Electric ferries rely on these batteries to store energy, which is then used to power electric motors that drive the vessel. One of the key advantages of electric ferries is their efficiency. Electric propulsion systems are far more efficient than diesel engines, as they can convert a higher percentage of stored energy into actual propulsion. This means that electric ferries not only reduce emissions, but also require less energy overall to operate. The environmental benefits of electric ferries extend beyond reducing greenhouse gas emissions. Traditional diesel-powered ferries produce significant amounts of air pollution, including particulate matter and nitrogen oxides, which are harmful to both human health and the environment. Electric ferries, on the other hand, produce no emissions at the point of use. This makes them especially beneficial in urban areas or sensitive ecosystems where air quality is a major concern. Additionally, electric ferries reduce noise pollution, which can have a positive impact on marine life. Studies have shown that underwater noise from ships can interfere with the communication and navigation of marine animals, particularly mammals such as whales and dolphins. The first large-scale adoption of electric ferries occurred in Norway, which has become a global leader in electric maritime transportation. The country introduced the world's first fully electric car ferry, Ampere, in 2015. Since then, Norway has rapidly expanded its fleet of electric ferries, driven by government incentives and stringent environmental regulations. The success of Norway's electric ferry program has encouraged other countries to follow suit, with electric ferries now operating or in development in countries such as Denmark, Sweden, and even the United States. In many cases, governments are offering subsidies to ferry operators to offset the high initial cost of transitioning from diesel to electric ferries. Despite the many advantages of electric ferries, there are still challenges to widespread adoption. One of the main obstacles is the high upfront cost of electric ferries and the necessary charging infrastructure. While electric ferries are cheaper to operate in the long term due to lower fuel and maintenance costs, the initial investment can be prohibitively expensive for smaller ferry operators. Another challenge is battery life and range. Currently, the range of electric ferries is limited by the capacity of their batteries, which means they are best suited for shorter routes. Advances in battery technology, such as the development of higher capacity batteries and faster charging systems, are expected to address these issues in the coming years. Another potential limitation is the availability of renewable energy to power electric ferries. While electric ferries themselves produce no emissions, the overall environmental impact depends on how the electricity they use is generated. If the electricity comes from renewable sources such as wind, solar, or hydropower, the environmental benefits are maximized. However, if the electricity is generated from fossil fuels, the reduction in emissions is less significant. This highlights the importance of transitioning to clean energy sources in parallel with the electrification of transport. Looking to the future, the impact of electric ferries could be profound, not only in reducing emissions, but also in reshaping the maritime industry. As battery technology improves and costs come down, it is likely that more countries will adopt electric ferries for both public transportation and commercial shipping. In addition to environmental benefits, electric ferries could lead to more cost-effective maritime transport, particularly in regions where fuel costs are high. Moreover, the development of electric ferries is part of a broader shift towards sustainable transportation that includes electric cars, buses, and trains. Together, these technologies have the potential to significantly reduce global carbon emissions and create a more sustainable future. Article 4. The science of gravitational waves and their detection. Gravitational waves are ripples in the fabric of spacetime caused by some of the most violent and energetic processes in the universe. Predicted by Albert Einstein in 1915 as part of his general theory of relativity, gravitational waves remained purely theoretical for almost a century. They were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory at LIGO, confirming a major aspect of Einstein's theory and opening a new window for understanding the cosmos. Einstein's theory suggests that massive objects cause a distortion in spacetime, and when these objects accelerate, they create waves that propagate outward at the speed of light. These waves stretch and squeeze the space they travel through, but they are extremely weak. By the time they reach Earth, even the most powerful gravitational waves only cause distortions at the atomic level. This makes them incredibly difficult to detect. The LIGO experiment was crucial for detecting gravitational waves. Using two detectors located in Louisiana and Washington, LIGO relies on laser interferometry to measure minuscule changes in distance caused by passing gravitational waves. When a gravitational wave passes, it changes the relative lengths of two perpendicular arms in the detector, which are each 4 kilometers long. By measuring the interference pattern of laser beams that travel down these arms, LIGO can detect even the tiniest changes in distance, on the order of 1/10,000th the width of a proton. One of the key challenges in detecting gravitational waves is eliminating noise. Earth's surface is teeming with vibrations from seismic activity, weather, human activity, and even passing traffic. LIGO has to filter out these disturbances to isolate the signal of a gravitational wave. Advanced techniques such as seismic isolation and noise reduction algorithms are used to minimize interference and improve sensitivity. The first direct detection of gravitational waves in 2015 was a result of two black holes merging about 1.3 billion light-years away. This event, known DWO 914, released more energy in the form of gravitational waves than the combined light output of all the stars in the observable universe during that moment. The detection not only confirmed the existence of gravitational waves, but also provided evidence for the existence of binary black hole systems. Since the 2015 detection, LIGO, along with its European counterpart Virgo, has identified dozens of gravitational wave events, most of them resulting from the merger of black holes or neutron stars. These observations are providing unprecedented insights into the nature of black holes, neutron stars, and the fundamental forces that govern the universe. Gravitational wave astronomy is still in its infancy, but the potential is immense. Unlike electromagnetic radiation, which can be blocked or absorbed by objects in space, gravitational waves pass through matter virtually undisturbed, allowing scientists to observe events that would otherwise be invisible. As the sensitivity of detectors improves, we may one day detect gravitational waves from the early universe, potentially shedding light on what happened mere moments after the Big Bang. Future missions, such as the planned Laser Interferometer Space Antenna (LISA), aim to detect gravitational waves in space where there is less interference from Earth-based noise. By operating in space, LISA will be able to detect low-frequency waves, such as those produced by the merger of supermassive black holes, which are beyond the reach of current ground-based detectors. The detection of gravitational waves represents a major scientific breakthrough comparable to the discovery of radio waves or X-rays. It opens up a new way of observing the universe, complementing traditional telescopes that detect light. With each new gravitational wave event, we gain deeper insights into the nature of spacetime, gravity, and the universe's most extreme phenomena.